When talking about energy, it's inevitable to start talking about units of energy and the numerical aspect of energy. And so we will start talking about units of energy. There are different units depending on the context where you will be using the concept of energy. So in science, the most common unit may be the joule because it's in SI units. But in nutrition, for example, the calories, or even in chemistry, you may be using calories. And it's important that you remember what the definition of a calorie is. By definition, a calorie is the energy needed to raise the temperature of 1 gram of water, 1 degree. Okay? So if you have 1 gram of water to raise it 1 degree, okay, you have then 1 gram of water still. That's the energy that it takes. The energy that it takes for this transformation is, by definition, 1 calorie, and so it's well known, and it's this amount of joules. Okay, of course, 1 kilojoule is 1,000 joules. Remember the kilo prefix. And something that you may or may not know is what a calorie with a capital C is. A calorie is the same as a kilocalorie. So sometimes that may be confusing because if you look at your food, they may contain calories in capital C. That's not the same as calorie lowercase. A calorie capital C is 1,000 calories lowercase c. Okay, so let's do some trivial problem solving, a little bit of transformations that may give context to all these different units of energy. In this problem, we say that a can of soda contains these many calories, and again, notice that it's a capital C, calorie, and you drink 2 of them. You shouldn't, but say that you do it, alright? So how many joules are you consuming each day? And how many kilojoules? So you need to set up a factor conversion, and you may want to start, there are many ways to do this, but if you say that you drink 2 cans, that's what I will start, and you know that 1 can contains 183 calories, and it's asking me how many joules, so I need to jump into lowercase calories, and I know that 1 calorie is 1,000 lowercase calories, and now I transform lowercase calorie into, I'm going to use this number over here, into joules, 4184 joules, and I plug this into a calculator, and I believe that this is 1531344 joules. Okay, or what's the same, 153.344 kilojoules. All right, so I moved the dot to the left 3 points. Okay, that was kilojoules and joules. So is that a lot? Is that not much? Well, you may be more familiar with the term calories, so this is why in nutrition we will keep using the capital C, calories. So the next question is, how many degrees would 1 gram of water increase? In other words, what it's asking here is, how many calories is that? Because remember, the definition of lowercase calories is, and I'm going to point it out here, is the energy needed to raise the temperature of 1 gram of water. This is what this is asking. So I just need to obtain the number here. So if I multiply 2 times 183 times 1,000, that would be, if I'm not mistaken, 366,000 calories. Okay, so which is the same as 366,000 degrees that you could increase with this energy 1 gram of water. So not bad for 2 cans of water. That's a lot of temperature to increase 1 gram of water. Okay, and so that may give you a little bit of a perspective how much energy we're consuming through our ingestion of food. And the last question is, for how long could you keep a 60-watt light bulb on? And it says that 1 watt, and maybe you may not know, it's the unit of power, which unit of power is energy over time, so joules per second. So it says for how long you could keep, with 2 cans of soda, you could keep that light bulb on. Well, if I can just use this amount, 1,344 joules, and the light bulb requires 60 joules in 1 second, this will give you the time that you need to that you can have the light bulb on, which I believe is around 25,000 seconds. I think if I did the calculation right, it's 25,500 to 2 seconds. Okay, so again, not bad for 2 cans of soda. That's a long time to keep the light bulb on.